Hello, today we will talk a little bit about set theory and particularly about countable sets. Let us consider some set A. Anything, functions, sequences, trees in the park, whatever you like. And we call this set countable. If we can establish one-to-one correspondence between elements of A and natural numbers. If we can establish one-to-one correspondence between this and this set. What does it mean? It means what each element in A has an unique correspondent among natural numbers, so has some particular number, and each number has a unique correspondent in A. So there is one element in A with number, I don't know, 100. In other words, simply saying, A can be just numbered. So it is infinite set, but can be numbered. So in fact, A is some sequence. In other terms, so maybe it's easy to understand if we use some computer terms. A is countable if we can develop a computer code algorithm what takes as input element of A, and in output it gives a number of this element, and our algorithm works for each element in finite number of steps. So it cannot work infinitely, and each element can need to obtain some particular number. Another definition: A is finite if it consists of finite number of elements. For example, set of trees in the park is obviously finite, because there are many trees, but finite number. And we say what A is less or equal and countable, and write something like this, if A is finite or countable. Finite or countable set is called less or equal than countable. Let's consider an example. First, an obvious example, set of natural numbers. Of course, it is infinite and it is countable, obviously. Let's consider more complicated example. Set of positive rational numbers or fractions m divided to n, where both m and n are natural. Of course, this set is much wider than n, but nevertheless it is also countable, and let us prove it. We start with all fractions with denominator 1. So 1 divided to 1, 2 divided to 1, 3 divided to 1, 4 divided to 1, and so on. So actually it is natural numbers. Then all fractions with denominator equal to 2. And so on. By doing this, we finally can write down each of these fractions. So each fraction will appear, would appear in my whiteboard if it is infinitely large. And let us start numbering. So here is number 1. Let's move to the right. Number 2. Then by diagonal to the left and down. Number 3. Then move down. Number 4. Next move to upright and to the right. And first we face the number what already was met. So 2 divided to 2 is obviously is 1, and we already counted it. So we just pass it by and come here. So this is our next number, number 5 in this case. Continue to the right. Next. Here, 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 and so on. Finally, each fraction will get a unique number. And please notice very interesting things. So we already discussed what this set of fractions is much wider than a set of natural numbers. Nevertheless, there is a one-to-one correspondence between these two sets. This algorithm sets one-to-one correspondence between small sets and this one what is much bigger. It's one of specific features of infinite sets. So you cannot establish one-to-one correspondence between set of 2 elements and set of 3 elements. But if infinitely many elements, you can do it in some cases. Before formulating next theorems, let us introduce some 2 operations on sets. Actually, of course, you know this definition. Let us have some set of indices. It can be finite, countable, non-countable, everything what we like. And let us consider some family of sets. So, once again, lambda can be equal to 1, 2, natural numbers, real numbers, anything. And the union is defined of this family is defined like this. X belongs to the union of this family of sets if X belongs at least to one of these sets. And similarly, we can define an intersection. So X belongs to an intersection of this family if it belongs to every set. For each index, X belongs to V. Now we can formulate the theorem. Let our set of indices is less or equal than countable, and each set of this family is also less or equal than countable. Then the union of all sets is also less or equal than countable. So the union of less or equal than countable of less or equal than countable sets is less or equal than countable. Very easy. Proof. We will use the same idea as for the fractions. So first first of all, set of indices can be represented as some sequence of 1, of 2, and so on. Finite or infinite. Finite if it is finite set, or infinite if it is countable. And each set also can be represented as a similar sequence. A of 1 is A of 1, 1, A of 1, 2, A of 1, 3, and so on. The same for A of 2. in some line, instead of infinite sequence, we can have finite number of elements, but it doesn't spoil our algorithm. And let's do the same. First element, second, third, fourth, fifth, and so on. If in some line we do not have more element, we just do nothing and continue from this just to the next one. Found an error. And finally, we can count all these sets, and here all elements of this union will appear if our whiteboard is big enough. Okay. One more definition. Let us have some finite family of sets. So, in this family, only finite number m of representatives. And the Cartesian product of these sets is defined like this. It is a set of ordered vectors and each element, each our coordinate belongs to the corresponding set. For example, R2 is a Cartesian product of R by itself. And our next theorem is connected with Cartesian products. If we have this finite set of finite family of not more than countable sets, then the Cartesian product of these sets is also less or equal than countable. Proof. Let us use principle of mathematical induction. And we begin with a case k equal to 2. Sorry. We have two sets. Set A1 would consist of not more than countable number of elements, A1, A2, and set A2. It's more convenient to denote element by B. B1, B2, BK, and so on. Maybe finite, maybe infinite series. Then A1 multiplied by A2 can be represented. It's a set of pairs, one element from A1, one element from A2. So we can arrange it like this. So first we write all pairs with second element B1. Next, second element B2. And so on. So once again, by doing this, we sooner or later will write down each such pair, and then use familiar procedure. Not here, but element A1, B3, yeah, and so on. So finally, this Cartesian product of two sets is countable, less or equal than countable. And let's assume that we have proved it for k minus 1. Let's prove it for k. It is a set of k-dimensional vectors, and we can represent these vectors as in this form. So k minus 1 dimensional vector multiplied by last dimension. And this set is less or equal than countable, because this is countable by our assumption. Product of two less or equal than countable sets is less or equal than countable. We have proved it. So we have proved everything in this theorem. These two theorems, they are very practically useful, and they can help us to extend our examples of countable sets. For example, set of all rational numbers can be represented as a uniform of negative rational numbers, 0, and set of positive rational numbers. We have proved what this set is countable. Similarly, it can be proved for this set, and 0 is this set is obviously finite. So uniform union of three sets, 2 countable and 1 finite, is countable. Next example. Set of d-dimensional vectors with rational coordinates is also countable, because it's a product of two, so set of rational numbers by itself, q times d times. So it is countable. But we can find also non-countable sets, and in order to assure you with this, I set last example in this paragraph. Let's consider closed segment 0, 1 of rational numbers. So it is a set of all elements, all real numbers, sorry, all real numbers what are between 0 and 1. So all real numbers what are situated between 0 and 1. And we prove what this set is non-countable. Let's prove it. We will use the reasoning by contradiction. Let's assume what it is countable, so it can be represented as some sequence. Well, of course it is infinite, so this sequence also should be infinite. And let us do the following operation. Let's divide our segment 0, 1 into 3 equal parts. And let's consider this number A1. It can fall into one of the segments, or if it's very lucky, it can fall on the boundary, so it will belong to simultaneously to 2 segments, but it cannot belong simultaneously to all 3 segments. So let's us assume what this segment, what we call x1, y1, doesn't contain a1. Well, let us write it down. So x1, y1 belongs to our initial segment 0, 1. The length of x1, y1 is equal to 1/3, and a1, let us a1 doesn't belong to x1, y1. We split our new segment x1, y1 also into 3 equal parts, and do the same procedure with a2. So a2, actually it can be outside this segment at all, so it can be here or here, or it can fall into one of these small parts, or to 2 parts if it is on the boundary, but cannot fall into all 3 parts simultaneously. So we can find the new segment x2, y2 with such properties. So this segment doesn't contain a2, and so on. After several steps, we can have we will build a segment xk, yk. Such what the length of this segment is 1 divided to 3 in power k, and ak doesn't belong to this segment. And so on. So we have the sequence of embedded segments. So all our segments belong to previous one, and the length of these segments converges to 0, and all segments are closed. We will use one fundamental theorem of mathematical analysis of real numbers called theorem about embedded segments, and it says what each such sequence of embedded segments with the length convergent to 0 and segments need to be closed has an non-empty intersection. So there is a element A star what is belongs to the intersection of these intersection, it means what A stars belong to each segment. Next, go back here. A star, obviously an element from our unit segment. And so, according to our assumption, it should get some number. So, there is an element from this sequence such that it coincides with a star. But this element, we build these segments in such a way that this element doesn't belong to a segment xk or xm ym. And an element A star belongs to each segment, and of course to this one particular. So we have a classical contradiction. The same element need to belong to the segment and also cannot belong to it. So our assumption that all elements of this segment can be represented as some sequence is wrong, because we found another element that is not represented here. So segment 0, 1 of real numbers is indeed non-countable. That's all for now. Next we will use this in order to define new property of non-space.